revolutionary discovery just shattered 146 years of scientific assumptions about magnetism and electricity. Japanese physicists have accomplished what many thought impossible. They've successfully detected a mysterious electromagnetic phenomenon called the anomalous Hall effect in materials that shouldn't theoretically exhibit it. This groundbreaking achievement could completely transform how we design electronic devices and sensors in the coming decades. But here's where it gets controversial. This discovery directly contradicts what textbooks have taught physics students for generations about the relationship between magnetism and electrical conductivity. Let's step back to understand why this matters so much. Way back in 1879, an American scientist named Edwin Hall made a fascinating observation. When he passed electricity through a conductor while applying a magnetic field, something unexpected happened. A voltage appeared across the material in a completely different direction. Picture water flowing through a pipe, but when you apply pressure from the side, the water somehow creates a force pushing sideways. That's essentially what Hall discovered with electric charges. This Hall effect became incredibly important for understanding how electricity and magnetism interact. Scientists quickly realized they could use this phenomenon to measure magnetic fields, determine the properties of materials, and even create sensors that we still use in our cars, smartphones, and countless other devices today. Then, things got more complicated. Researchers noticed that magnetic materials displayed a similar but distinctly different version of this effect, which they dubbed the anomalous Hall effect, or AHE. Unlike the regular Hall effect, this anomalous version seemed to follow different rules and appeared much stronger in certain situations. And this is the part most people miss. For over 140 years, scientists believed this anomalous effect could only occur in materials that were already magnetic. It seemed logical. After all, if you need magnetism to create the anomaly, shouldn't the material itself need to be magnetic? Enter Associate Professor Masaki Uchida and his team from the Institute of Science, Tokyo. These researchers decided to challenge this fundamental assumption using an exotic material called cadmium arsenide, CD3Ace2. This substance belongs to a fascinating category known as Dirac semimetals, materials where electrons behave like they have no mass, similar to particles of light. What makes Dirac semimetals so special? Their electrons exist in unique energy states called Dirac points, where they can move freely in all directions without the usual restrictions that affect electrons in ordinary materials. Think of it like the difference between walking through a crowded hallway versus sprinting across an empty field. The electrons in Dirac semimetals have that kind of freedom. The Japanese team employed a clever experimental strategy. They grew incredibly pure, thin films of their cadmium arsenide using a sophisticated technique called molecular beam epitaxy, essentially building the material atom by atom in a vacuum chamber to ensure perfect crystal structure. Then came the crucial part. Instead of applying a magnetic field perpendicular to the material, which would create the ordinary Hall effect, they applied it parallel to the surface, creating what scientists call an in-plane magnetic field. But here's where the controversy really heats up. When they applied this sideways magnetic field, something remarkable happened. The Dirac points in the material transformed into whale points, even more exotic electron states that break certain symmetries in the crystal structure. This transformation effectively suppressed the ordinary Hall effect while amplifying the anomalous version. The results were nothing short of extraordinary. Not only did they observe the anomalous Hall effect in their non-magnetic material, but they detected a giant version, meaning the effect was much stronger than anyone had predicted. Through careful analysis, they determined that this phenomenon originated from something called orbital magnetization. To understand orbital magnetization, Imagine electrons as tiny spinning tops that also orbit around atomic nuclei, like planets around the sun. Scientists had long assumed that the anomalous Hall effect came from the spin part, the intrinsic rotation of the electron. However, this new research suggests it actually comes from the orbital part, the circular motion of electrons around atoms. This distinction might seem academic, but it has profound implications for our understanding of quantum materials and electromagnetic phenomena. If the effect comes from orbital motion rather than spin, it opens up entirely new possibilities for controlling and manipulating these effects in technological applications. Uchida emphasizes the broader significance. Our approach isn't limited to just Dirac semimetals. This technique could work with many other types of materials, potentially revolutionizing how we think about Hall effects in general. The practical applications could be game-changing. Current Hall sensors and similar devices rely on magnetic materials, which limits their efficiency and operating conditions. If engineers can harness the anomalous Hall effect in non-magnetic materials, they could create sensors that work better, consume less power, and function in environments where traditional magnetic sensors fail. Now, here's the million-dollar question that's dividing the physics community. If this effect can appear in non-magnetic materials, what other impossible phenomena might be hiding in plain sight? Are we on the verge of discovering that many fundamental assumptions in condensed matter physics need complete revision? Some experts argue this discovery represents just the tip of the iceberg, suggesting that our understanding of quantum materials is far more limited than we thought. Others maintain that, while significant, this finding simply adds another tool to our existing toolkit, rather than overturning established principles. The research team believes their work will spark both fundamental research into the underlying physics and practical development of next-generation devices. They envision Hall sensors and related technologies that could operate more efficiently across broader temperature ranges and magnetic field conditions than anything currently available. What do you think? Is this discovery a revolutionary breakthrough that will rewrite physics textbooks? Or simply an interesting addition to our existing knowledge? Could materials we've dismissed as non-magnetic actually harbor hidden electromagnetic properties that could transform technology? The scientific community is actively debating these questions, and the answers could shape the future of electronics and quantum computing. This research certainly challenges us to reconsider what we think we know about the fundamental relationship between magnetism, electricity, and matter itself.